Okay, we will start our class today and continue with the random variables. So, last time we have talked about the random variables. So, we are going to discuss some useful random variables. In fact, there are a variety of many different random variables, and those are the ones that are commonly encountered in communication engineering. So um, we have uh, Bernoulli random variables. That is the binary value random variable, and it has two values, two possible values, and with probability p and 1 minus p. And then we also mentioned that we are very interested in two things. The first thing is the expectation. Sometimes we also call it mean. Uh, we oftentimes we also call it the mean of a random variable, and this is the variance. So um, here is the equation, and then the Bernoulli random variable. Bernoulli is the summation of, I'm sorry, uh, binomial. The binomial is the summation of Bernoulli random variable. So it has this probability density function and also the mean and variance. Okay, and then the next thing is the uniform. Uniform distributed something like this. It's distributed with the value a and b, and it has this density 1 over b minus a. That is the uniform random variable. Okay, and then Gaussian random variable. We are very used to this Gaussian random variable, and then the mean and variance. Okay, and this is very common. And if we take a look at the distribution, it looks like we have a distribution and then CDF. Those are the two distribution we are also very interested, and that represents this represents the probability density. For example, if you draw a point here, you are making uh, a point that is the probability density. But if we look at the CDF, when we look at the CDF, if you make a point here, what actually means for this point is the probability that the realization of the random variable is going to be below this area. It's going to be below this threshold. So this represents the probability. But this is not a probability. This is the probability density. So there's a difference. Okay, so the CDF, any point on the CDF represents a probability. A probability for the event that realization is going to be below that threshold. So that is the event probability. Okay, and then um, if we have a distribution that is a Gaussian distribution, and anything larger than that will be described by a Q function. Anything below will be described by a Q function. So we have the details in previous talk. So we're going to go faster on this one. And also there's a table for Q functions. So for example, Q of 0.5, uh, Q of 0, I'm sorry, Q of 0 is 0.5. If we look, it's actually if you see that for a Gaussian distribution, anything larger than 0.5, anything larger than 0 is 0.5, right? Because it's just centered. The probability density function is centered around 0 and 0.1, something like that. And as you go larger, you go x goes larger, then the probability becomes smaller and smaller. And so this is the value of a Q function. And actually, in a lot of the mathematical tools, for example, the MATLAB or Python mathematical packages, you can easily find out there is a function for Q function. So you just call the Q function and it gives you the numerical outcomes for Q function. So that is the Q function. That is a Q function. But in all times, when people do not have the tools, what they need to do for this is to check either this table or then you resort to numerical approach. For example, the Newton method or whatever numerical approach you're going to use for this calculation for this Q function. And then arrow function, complementary arrow function. This complementary arrow function defined as this. So actually I should put a, a triangle here. It's a defined function, and the relationship is q of x equal to 1/2 arrow function of this, or arrow function can be expressed in terms of the q function. Okay, then chi-square random variable. The chi-square random variable is a summation of Gaussian random variable, and it has to be IID, independent and identically distributed, and also zero mean Gaussian random variable with common variance. So you will this is in fact there's a triangle to make it a notation. So x is defined as summation of xi square, and then x is a chi-square random variable with n degrees of freedom. Okay, so the number of random variables is stands for chi-square. Stands for the degree of freedom in the chi-square. So let's say you have summation of 10 Gaussian random variable, then you'll be degree 10. If it's 15, then it's 15, or whatever numbers you want to use. So this is kind of the summation of Gaussian square. So the PDF of this random variable is given by this. Okay, so let's take a look. It's p of x equal to 1 over 2 to the n divided by 2 and gamma n divided by 2 sigma n, and x n by 2 divided by 2 minus 1 and exponent minus x divided by 2 sigma square. So let's just get a sense of what it looks like, and it's for x larger than 0. Otherwise is what? Otherwise means anything other than that statement, right? So this means x smaller than 0. Otherwise, so it's very clear that the chi-square distribution is a positive random variable, right? How come? If we take a look, it's actually a summation of x I squared. And if you imagine you have a summation of something square, it's got to be positive, right? You sum up squares. Squares are positive, and you are doing summation of positive numbers. As a result, it's going to be positive. So you can see that the probability density function has a value for positive domain, and for negative domain, it's always 0. And that gamma x is the gamma function defined by this. And I like to mention that this is called spatial functions. We call it spatial functions. And it has a whole category, as I mentioned. It has a whole category of spatial functions. We're going to have some of them later on. But in this class, we're just going to have some of them, but it has hundreds. If, if you do more complicated problems in engineering, you're going to encounter a lot of different spatial functions. And there's in fact a book with hundreds of pages talking about spatial functions. Okay, but we only need to notice some of them, those that are particularly useful in communications. Okay, and the gamma function has some properties. For example, the factorial, the gamma of 1, gamma half, and gamma n divided by 2 plus 1 equal to this n factorial, n divided by 2 factorial, and for n even and positive. If n is odd and positive, then it will be something like this. And in any case, it has a factorial structure, like n divided by 2 or something like that. It has a factorial structure. Okay, so that is the gamma function. Then the CDF, when n is even, in other words, n is equal to 2m with m being an integer, then n is an even function, and then it has a closed form given by 1 minus this, of course, for x larger than 0, as before. 1 minus exponent 2 minus x divided by 2 sigma squared, summation of 1 over k factorial, parenthesis x over 2 sigma squared to the k is 0 to n minus 1. And recall that alpha is what? Alpha is the, sorry, this is a sigma, it's a tiny font, but it's a sigma. Sigma is the standard deviation. The standard deviation for the Gaussian random variable. Okay, and the mean and variance are always of our interest. So the expectation is n sigma squared. The variance is 2n sigma to the 4. So we have expectation and variance. That is of our interest. And the special case for a chi-square random variable with 2 degrees of freedom is of particular interest, and the PDF is given by P of x equal to this 0, 1. This is for x larger than 0, 1 divided by 2 sigma squared exponent minus x over 2 sigma squared. So that is the PDF for degree 2. And That is also the exponential random variable with mean equal to 2 sigma squared. The chi-square random variable is a special case of a gamma random variable. A gamma random variable is defined by a PDF of the form p of x equal to 0, otherwise, or for x larger than 0 is lambda x alpha minus 1 minus lambda x divided by gamma alpha. And this gamma alpha is larger than 0. And the chi-square random variable is a gamma random variable with lambda equal to 1 over 2 sigma squared and alpha equal to n divided by 2. So if we take a more general view on this, this is in fact a function can always be generalized, right? Generalized and special case, generalized versus special case. So gamma random variable is a more generalized version, and then in that context, we can see chi-square as a special case for gamma. Okay, and then we go to this non-central chi-square random variable. Non-central chi-square random variable. The non-central chi-square random variable with n degree of freedom is defined similarly to chi-square, in which xi's are independent Gaussians. The independent Gaussian. So we have to mention that it always has to be independent. Uh, Correlated cases are hard to deal with, which we'll talk about later. But we deal with independent cases first in this subsection. So with common variance, sigma squared. But, but notice that with different means denoted by mi, it has different means. Okay, so it's uh, rather different than before in terms of the means. What happens before? For the regular chi-square, it has 0 mean. But here we have mi as a mean, which is not 0. So the random variable has a PDF of the form here. So it's for x larger than 0, it's 1 over 2 sigma square x divided by s square, n divided by 2 to 4, and then exponent minus s squared plus x divided by 2 sigma square, and I n divided by 2 minus 1 of s divided by sigma square square root of x. So that is for x larger than 0. And then otherwise, meaning x, of course, smaller than 0. Okay. So here is a figure that shows the form for chi-square. So if that is the chi-square, we take a look at the chi-square for different values of degree of freedom, and it plots for sigma equal to 1. So you can see that n equal to 1 is something like that, n equal to 2, something like that, n is 3, 4, 5, 6. So what do you observe here? If you look closely, n equal to 1, meaning that you have a summation of one Gaussian variable. As a result, it has more density around 0. But if you have 2, it's wide spreading, right? Spreading out. 3, spreading out. 4, even more spreading out. 5, 6. So as n goes larger, meaning that you are doing summation for more Gaussian random variables. If you are doing summation for more Gaussian random variables, the probability density tends to spreading out to the right, which is reasonable. Which is reasonable. Just because you are doing summation for a lot more Gaussian random variable. Okay. Okay, so let's go back for this non-central. So that S is defined as, because we have parameters for S, then sigma, right? But sigma is known for what? Sigma is the standard deviation. Sigma square is the variance for that Gaussian. So we had no problems with the sigma. But for S, now the S is defined as summation of mean square, right? This is the mean for the Gaussian, and you take the square, and you do the summation. You take square, summation, and then square root. That is the S. And one more thing about this I, again, it's a special function. It's a special function. So alpha I, alpha x is the modified Basel function of the first kind. Modified Basel function of the first kind. Again, this is one of the special function in the category of special function order alpha given by this. So let's see, if you have I n divided by 2, you have a subscript n divided by 2 minus 1, and its argument is something like that, and S has been defined. S has been defined. So we have subscript alpha, which is equal to n over 2 minus 1. Okay, so that is alpha. And argument S, you put it in, and it's a summation of this x divided by 2 alpha plus 2k over k factorial gamma alpha plus k plus 1 for x larger than 0. So just a bit of reminder, that factorial, if you have 3 factorial, it's equal to 3 divided 3 multiplied by 2 multiplied by 1. Okay, that's 3 factorial. So if you have k factorial, it's k multiplied k minus 1 multiplied k minus 2, so on and so forth. So that is the k factorial. And summation, we can see that the k is going from 0 to infinity, and it's a it's a it's a series, right? It's a series. A series with what? With infinite number of terms. So it's a bit difficult to understand because you have a now you are challenged with the summation of infinite terms. So again, if we have to do the exact number for I alpha of x, it's just be impossible because you have infinite terms. But we can approximate it to certain degree of accuracy by numerical approaches, or you skip some terms. You can see the factorial goes larger and larger. So when you go, when that number of k goes up to a certain level, this number is just very small because it's in the numerator, and since it's very small, it can be ignored. That's the way to do approximation, or use computers to do this iteratively up to a large number of k, and that's a reasonable approximation. Okay, so gamma is a gamma function. and I0 can be written as this one just because the subscript alpha is equal to 0. So that whole business simplifies to this. Okay, and then there are other ways to approximate it, or you can use other kinds of expressions. Okay, but after all, whatever we do, we are unable to get a closed form. Okay, so then the CDF of this random variable when the n is even, and it's written in this way. The CDF, we have to emphasize, this is a CDF. Okay, it's equal to 1 minus Q function. No, not Q function. This is a Q sub m, and then argument with S over sigma, square root of X over sigma, and 0 otherwise. If its PDF has 0 for X smaller than 0, then its CDF must be 0 for X smaller than 0, because its PDF has 0 value in the negative region. Okay, so and then this Q AB is a generalized Markov Q function, and it's defined this way. So Markov Q function QMAB is defined as the integration of this and exponent and then Basel function. Right? This I is a Basel function, as we did, right? Okay, so we can define Q1 AB as this. So this integration simplifies to Q1. Okay, and it has some specific values, Q1 x0 or Q1 0x. The most important thing is the non-central chi-square random variable, mean and variance, is given by expect of x equal to n sigma square plus s square. Variance of x is 2n sigma to the 4 plus 4 sigma square s square, and then s is defined as before. Okay, so I think that's the end of this session, and we will continue next session.